Small turboprop engines have arrived, and many are claiming it is the future of light aircraft propulsion. But can it challenge piston engines on fuel economy and cost?
Close your eyes and imagine. You're cruising at 20,000 feet in a single-engine turboprop, the horizon stretching endlessly before you. The engine purrs with a smooth, continuous whine. No vibration, no reciprocating violence. Just pure rotational power spinning at tens of thousands of RPM. Below you, piston-powered aircraft labor at lower altitudes, their engines hammering away with mechanical brutality, pistons slamming up and down hundreds of times per minute. This isn't science fiction, it's the promise that turboprop technology has tantalized us with for decades, and recent breakthroughs suggest it might finally become accessible to general aviation. The revolution at 20,000 feet. For over a century, piston engines have dominated light aircraft like an unshakable institution. They've powered everything from Cessna trainers to warbird legends, their familiar rhythm becoming synonymous with flight itself. But that dominance faces its first real challenge. In specialized applications worldwide, a new sound is emerging. The turbine's whistle, once reserved for jets and airliners, now spinning propellers on smaller aircraft, with breakthrough technologies promising to solve the efficiency problems that have kept them from mainstream adoption. The reliability numbers tell a compelling story. The Pratt & Whitney PT-6A turboprop achieves time between overhauls of 3,600 hours standard, extending to 6,000 hours on some variants compared to the typical 2,000 hours for piston engines. These turboprops routinely operate for thousands of hours with minimal, unscheduled maintenance. Meanwhile, piston engine owners face regular cylinder work, magneto replacements, and exhaust repairs as routine operating expenses. But here's the catch that's kept turboprops from conquering general aviation: fuel consumption. Traditional small turboprops burn 0.55 to 0.65 pounds of fuel per horsepower hour, while modern piston engines achieve 0.42 to 0.45, with some diesel variants reaching an impressive 0.36. This efficiency gap has been the fortress wall protecting piston dominance. Until now, the empire under pressure. For 8 decades, Lycoming and Continental ruled general aviation with engines that traced their lineage to the 1930s. These horizontally opposed power plants became the backbone of civilian flying, reliable enough, powerful enough, and most importantly, affordable enough for average pilots. The 0320, 0360, and 0540 series engines powered millions of flight hours. Their designs refined but fundamentally unchanged since Eisenhower was president. The first cracks in this empire appeared with environmental concerns over leaded aviation gasoline. While cars abandoned lead in the 1970s, aircraft engines clung to 100 LL low-lead A gas, still containing 2.12 grams of lead per gallon. Environmental agencies worldwide began pressing for alternatives, but the installed base of engines requiring high-octane leaded fuel seemed immovable. Then Rotax arrived. From Austria with a different philosophy, their 912 series engines, derived from motorcycle technology, brought liquid cooling, gear reduction, and electronic ignition to aircraft. Burning regular automotive gasoline, these engines achieved better fuel economy than traditional aircraft engines while weighing significantly less. Suddenly, the old guard faced competition from outside their comfortable ecosystem. The real disruption came from diesel technology. Continental's CD100 series engines, based on Mercedes-Benz automotive designs, burn Jet A fuel while achieving specific fuel consumption around 0.36 pounds per horsepower hour, nearly 20% better than traditional avgas engines. Diamond Aircraft built entire model lines around these engines, proving that piston technology could evolve when pressed. Why small turbine struggled engineers have dreamed of scaling turbine technology down to light aircraft since the 1950s. The appeal was undeniable. Eliminate the reciprocating masses, the complex valve trains, the temperamental carburetors. Replace them with smooth rotation, simple architecture, and proven reliability. The physics, however, proved cruel to small turbines. As components shrink, The clearance between rotating blades and stationary housings remains nearly constant, meaning proportionally more compressed air escapes uselessly. A large turbine might lose 1% of compressed air to tip leakage. A small turbine might lose 5%. This geometric reality alone creates a massive efficiency penalty. The Reynolds number problem compounds the challenge. This dimensionless value describes the relationship between inertial and viscous forces in fluid flow. Smaller blades operate at lower Reynolds numbers, meaning the air behaves more like honey than water, dragging, swirling, creating losses at every turn. The same blade design that works brilliantly at airline scale becomes aerodynamically compromised at general aviation scale. Combustion efficiency suffers equally at small scale. Large turbines maintain stable combustion across wide operating ranges. Small combustors struggle with flame stability, especially at the partial power settings typical of cruise flight. While a piston engine might actually improve efficiency at reduced power, turboprops see dramatic specific fuel consumption increases when throttled back. For decades, these physics seemed insurmountable. The Allison 250, now Rolls-Royce M250, found success in helicopters and specialized applications, but its fuel consumption made it impractical for most fixed-wing uses. The engine burned roughly 0.60 pounds per horsepower hour, 50% more than comparable piston engines. The game-changing innovation. In a facility outside Paris, Turbotech achieved something the industry considered impossible: a small turboprop with near-piston fuel efficiency. Their TPR-90 engine claims specific fuel consumption of 0.45 pounds per horsepower hour, within striking distance of traditional aircraft engines, and better than many older designs. The secret is recuperation, capturing waste heat from exhaust gases to preheat compressed air before combustion. Industrial gas turbines have used this technique since the 1960s, but aviation applications seemed impossible due to weight and complexity constraints. A recuperator is essentially a heat exchanger operating in one of the most hostile environments imaginable: extreme temperatures, vibration, and the absolute necessity of reliability. Modern materials made the breakthrough possible. Inconel alloys, developed for aerospace applications, withstand the thermal cycling that would destroy conventional metals. Additive manufacturing enables geometries that maximize surface area while minimizing weight, folded passages that would be impossible to machine conventionally. Computer modeling optimizes every passage for maximum heat transfer with minimum pressure drop. The TPR-90 produces 130 horsepower from a package weighing just 78 kilograms, comparable to piston engines of similar power. It runs on Jet A, diesel, or even biofuels. Test pilots report turbine smoothness with fuel flows approaching their previous piston-powered aircraft. But this efficiency comes at a price, literally. Early estimates suggest the TPR-90 will cost approximately $100,000, roughly double a comparable piston engine. The hard mathematics of ownership. Aircraft ownership economics extend far beyond purchase price. A typical Continental IO360 costs around $45,000 new and requires overhaul at 2,000 hours for another $35,000. Between overhauls, expect cylinder work, magneto replacements, and exhaust repairs totaling $10,000 or more. That's $90,000 over 2,000 hours, $45 per flight hour just for the engine. But let's examine the hidden costs that make piston ownership even more expensive. Annual inspections on piston engines average $3,500, with compressions checks, oil analysis, and bore scope inspections adding another $1,200 yearly. Magneto 500-hour inspections run $800 each. That's $1,600 every 500 hours for the pair. Spark plugs need replacement every 400 hours at $50 each, $600 for a 6-cylinder engine. Oil changes every 50 hours cost $200, including filter and analysis. Over 2,000 hours, these minor expenses add another $18,000 to your operating costs. Small turboprops promise different mathematics. While purchase prices currently run double or more than piston equivalents, the maintenance savings are dramatic. Hot section inspections replace cylinder work. Electronic controls eliminate magneto problems. Single lever power management removes the possibility of detonation or shock cooling damage. Consider real-world operator data from a Canadian charter company that replaced their Continental-powered Cessna 206 with a Soloy turbine conversion. Their piston engine was costing $89 per flight hour in maintenance and reserves. The turbine conversion, despite its $400,000 price tag, reduced that to $52 per hour. At 500 hours, annually they save $18,500 per year. The higher acquisition cost pays for itself through reliability. Their dispatch rate improved from 87% to 96%, meaning more revenue flights and fewer stranded passengers. The altitude advantage multiplies these benefits. Turboprops maintain power as they climb, reaching their best efficiency at altitudes where piston engines struggle. At 18,000 feet, a turboprop might achieve its optimal fuel consumption while flying above most weather. A normally aspirated piston engine has lost 40% of its power and burns fuel inefficiently in the thin air. Turbocharged piston engines can maintain power, but add another layer of complexity and failure modes. Turbocharger replacements run $8,000 to $12,000 and often fail before TBO. Insurance companies recognize the reliability difference. Turbine-powered aircraft often qualify for premium reductions of 15 to 25% compared to piston equivalents. For commercial operators, this alone can justify the higher acquisition cost. A flight school operating a turbine-powered trainer reports annual insurance savings of $12,000 per aircraft compared to their previous piston fleet. The ability to dispatch reliably, especially in challenging conditions, translates directly to revenue. Weather cancellations drop by 30% when operators can climb above ice and turbulence, capabilities that piston aircraft struggle to match even with turbocharging. Two paths forward. The current market offers two distinct approaches to small turboprops, each with fundamental trade-offs. High-efficiency designs like Turbotech's recuperated engines achieve near-piston fuel consumption, but at premium prices and unproven long-term reliability. The recuperator adds complexity to what should be a simple engine, potentially negating the reliability advantage that makes turboprops attractive. The TPR-90's recuperator operates on a fascinating principle of thermodynamic recovery. The exhaust gas temperature leaving the turbine section reaches 650 degrees Celsius, energy that traditional turboprops waste entirely. The recuperator captures approximately 30% of this thermal energy, raising the compressed air temperature from 200 degrees Celsius to nearly 400 degrees Celsius before it enters the combustion chamber. This preheating means the engine needs 25% less fuel to achieve the same turbine inlet temperature. But this efficiency comes with engineering challenges. The heat exchanger must withstand thermal cycling from minus 40 degrees Celsius cold, starts to 650 degrees Celsius operating temperatures thousands of times without cracking, warping, or fouling. The alternative path, pursued by companies like Turb Aero and PBS Velka Bitesh, accepts higher fuel consumption in exchange for simplicity and lower cost. Their engines achieve 0.55 to 0.60 pounds per horsepower hour, about 30% worse than modern pistons, but with traditional turbine reliability and more accessible pricing around $60,000 to $70,000. PBS's TP100 engine exemplifies this philosophy. At 241 pounds producing 241 horsepower, it matches piston power-to-weight ratios while eliminating complexity. No cooling system, no ignition system, no valve train, just a compressor, combustor, turbine, and reduction gearbox. The company has delivered over 1,000 units primarily to UAV manufacturers, accumulating millions of flight hours that prove the fundamental reliability. Their latest variant, the TP100S, adds a second-stage turbine that improves efficiency by 8% while adding only 15 pounds, still not matching piston efficiency, but closing the gap. This bifurcation creates distinct market segments. Operators flying many hours annually might justify recuperated engines through fuel savings. Those flying less frequently might prefer simpler designs with higher fuel consumption but lower capital costs. Neither approach yet matches the overall economics of established piston engines for typical private owners flying 50 to 100 hours annually. The wildcard is ongoing development in ceramic materials and advanced manufacturing. NASA's Small Business Innovation Research Program recently funded 3 companies developing ceramic matrix composite recuperators that could operate at 750 degrees Celsius while weighing 40% less than metal equivalents. If these materials prove durable, recuperated engines could achieve 0.40 pounds per horsepower hour, better than most piston engines, while maintaining the weight advantages that make turboprops attractive for aircraft applications. The market response traditional engine manufacturers aren't standing still. Lycoming has partnered with Cobra Aero to develop small turboprops for the unmanned aerial vehicle market, a testing ground for technologies that might migrate to manned aircraft. Continental, through its parent company Aviation, has access to Chinese turbine development that could yield surprising advances. But the most interesting developments come from outside traditional aviation. Automotive suppliers, experienced with turbochargers and high-temperature materials from diesel development, see opportunities in aircraft propulsion. Electric vehicle companies view small turboprops as ideal range extenders for hybrid aircraft. A turbine running at constant, optimal speed charging batteries combines the energy density of liquid fuel with the efficiency and simplicity of electric propulsion. Several hybrid projects are already flying. A modified Pipistrel Panthera uses a small turbo generator to extend the range of its electric propulsion system. The combination delivers near-silent takeoffs from noise-sensitive airports, then efficient cruise powered by the turbine. It's a glimpse of how turboprops might enter general aviation, not as direct replacements for piston engines, but as components in hybrid systems that leverage the best of multiple technologies. Flight training organizations watch these developments carefully. The reduced pilot workload of turboprops, single-lever power control, no mixture management, no shock cooling concerns, could improve
safety while reducing training complexity, but the higher operating costs remain a barrier. Until turboprops achieve true fuel consumption parity with piston engines, most schools will stick with traditional power plants. Manufacturing revolution. The transformation in turboprop viability stems largely from manufacturing advances that seemed impossible a decade ago. Metal 3D printing enables internal cooling channels following optimal thermodynamic paths rather than manufacturing convenience. Components that once required dozens of parts brazed together now emerge as single pieces from powder bed fusion machines. This changes everything about engine development. Prototypes that once took months to machine can be printed in days. Design iterations happen at software speed rather than tooling speed. Small companies can develop engines without massive capital investments in production facilities. The democratization of turbine manufacturing breaks the monopoly of established aerospace companies. Electronic controls represent an equally dramatic advance. Modern full-authority digital engine control FADEC systems, derived from automotive applications, cost thousands rather than tens of thousands of dollars. They manage start sequences that once required careful pilot attention, prevent destructive overtemperature conditions, and optimize performance across all flight conditions. The pilot becomes a power requester rather than an engine manager. These computers are getting smarter. Machine learning algorithms analyze fleet-wide operational data to predict maintenance needs before failures occur. Software updates improve engine performance without touching hardware. One manufacturer recently increased power output by 3% through nothing more than optimized fuel mapping, impossible with mechanical fuel controls. Environmental and regulatory catalysts. The environmental case for turboprops grows stronger as regulations tighten. While they currently burn more fuel per horsepower than the best piston engines, turboprops run on unleaded Jet A available worldwide. The lead emissions from avgas affect communities around airports, creating political pressure for alternatives. The numbers are sobering. General aviation burns approximately 180 million gallons of 100 LL annually in the United States alone.
releasing 380 tons of lead into the atmosphere. A 2021 EPA study found elevated blood lead levels in children living within 1 kilometer of airports with significant piston aircraft traffic. Reed Hillview Airport in San Jose, California, became the flashpoint when Santa Clara County banned the sale of leaded fuel starting January 2022, effectively grounding many aircraft. The FAA intervened, but the message was clear: communities won't tolerate lead emissions indefinitely. Europe leads this charge. Several countries have announced plans to ban leaded avgas by 2030. While unleaded alternatives like G100UL are emerging, they cost significantly more than traditional 100LL. Jet A remains cheaper and more widely available than any aviation gasoline. For turboprops, the fuel infrastructure already exists at every airport serving commercial traffic. Switzerland's Federal Office of Civil Aviation has mandated a 50% reduction in lead emissions by 2030 and complete elimination by 2035. France follows with similar targets, offering tax incentives for operators converting to unleaded propulsion, whether electric, diesel, or turbine. The European Aviation Safety Agency has fast-track certification for unleaded fuel alternatives, but also streamlined supplemental type certificates for turboprop conversions, recognizing that fuel switching might be easier than fuel replacement. The carbon equation remains complex. A recuperated turboprop burning 10% more fuel than a modern diesel piston engine produces 10% more CO2. But if that turboprop enables reliable operation that keeps aircraft flying rather than sitting for maintenance, the per-mile emissions might actually decrease. The full life cycle analysis, including manufacturing and maintenance, hasn't been definitively calculated. Sustainable aviation fuel SAF compatibility gives turboprops another environmental advantage. While piston engines require specific octane ratings and careful fuel chemistry, turbines run on almost anything combustible. Current SAF blends reduce life cycle emissions by up to 80% compared to petroleum Jet A. Several turboprop manufacturers have certified their engines for 100% SAF operation, something piston engines cannot achieve without significant modifications. United Airlines' commitment to purchasing 3.4 billion gallons of SF will create supply chains that general aviation turboprops can leverage. Noise regulations increasingly favor turbines. The high-frequency whine of a turboprop, while distinctive, carries less distance than the low-frequency rumble of large displacement piston engines. Turboprops also eliminate the sharp impulse noise of exhaust valves opening, reducing community impact around airports. The transition timeline history suggests aviation engine transitions take decades, not years. Radial engines dominated into the 1950s despite horizontally opposed engines offering clear advantages. The inertia comes from multiple sources: existing fleet investment, mechanic training, parts infrastructure, and simple habit. Consider the numbers. Approximately 200,000 piston-powered general aviation aircraft operate worldwide, representing $40 billion in asset value. These aircraft have established maintenance networks, trained technicians, and proven operating procedures. The average general aviation aircraft is 40 years old. Many will fly another 40 years with proper maintenance. This installed base creates massive inertia against rapid change. Even if turboprop production started dominating tomorrow, the piston fleet would take decades to age out naturally. But modern transitions might happen faster. Information
Spreads instantly. Global supply chains can pivot quickly. Regulatory pressure provides deadlines that didn't exist in previous eras. If recuperated turboprops achieve their efficiency promises while maintaining reliability, the transition could accelerate dramatically. The unmanned aerial vehicle market provides a preview. Military and commercial drone operators rapidly adopted small turboprops despite efficiency penalties because reliability mattered more than fuel consumption for their missions. As these operators accumulate millions of flight hours, they're proving the technology at scales that general aviation couldn't achieve alone. General Atomics MQ-9 Reaper drones have logged over 7 million flight hours on their TPE-331 turboprops, more than many general aviation engine models accumulate in decades. This operational data flows directly into civilian certification efforts, de-risking the technology for aviation authorities. Historical precedent exists for rapid transitions when external factors align. The 1973 oil crisis drove a swift shift from large displacement engines to smaller, efficient designs in automobiles, a change that seemed impossible just years earlier. Aviation faced similar pressure but lacked alternatives. Now, with multiple turboprop options emerging simultaneously with environmental regulations, the conditions for rapid change are aligning. By 2035, industry analysts project 30% of new light aircraft deliveries will feature turboprop power. By 2045, that could reach 70%. These projections assume continued improvement in efficiency and reduction in cost, not guaranteed, but supported by current development trajectories. Frost & Sullivan's aerospace division predicts the tipping point will occur when turboprops achieve 0.42 pounds per horsepower hour at a price point within 50% of comparable piston engines. Based on current development rates, they project this convergence between 2032 and 2035. What this means for aviation's future. The turboprop revolution represents more than just different engines. It's a fundamental shift in how we think about aircraft propulsion. The simplicity and reliability enable new operating models. Aircraft could fly more hours annually with less downtime. Pilots could focus more on mission and less on engine management. Maintenance could become predictive rather than reactive. For manufacturers, the imperative is clear. Develop turboprop options or risk obsolescence. Textron, parent of Cessna and Beechcraft, has already announced turboprop development programs for their future aircraft. Piper, traditionally conservative, is exploring partnerships with engine manufacturers. The company that delivers an affordable, efficient four-seat turboprop will define the next generation of general aviation. For pilots and owners, the transition offers both opportunity and challenge. Early adopters of recuperated turboprops might pay premium prices, but gain competitive advantages in reliability and capability. Late adopters might get better technology at lower prices, but miss years of benefits. The choice depends on individual mission profiles, risk tolerance, and financial capacity. The parallel development of electric and hybrid propulsion adds complexity to these decisions. Should you invest in transitional turboprop technology or wait for electric aircraft that might be a decade away? The answer likely depends on your timeline. Turboprops are flying today. Electric aircraft, with practical range, remain largely experimental. What if breakthrough technologies suddenly made small turboprops as efficient as diesels? What if manufacturing advances dropped prices to parity with piston engines? The transition would accelerate from evolution to revolution. Every flight school would switch within an upgrade cycle. New aircraft would universally adopt turbine power. The piston engine industry would contract to a specialty market serving vintage aircraft. This isn't fantasy. Similar transitions have happened in other industries when technology reached inflection points. Digital cameras destroyed film almost overnight, once quality and cost reached critical thresholds. Smartphones eliminated dozens of separate devices once capability and convenience aligned. Aviation might be approaching its own inflection point. The question isn't whether turboprops will eventually power most light aircraft. It's whether current breakthrough technologies will make that transition happen in 1 decade or 3. For those paying attention, the signs are clear. The age of reciprocating aircraft engines, after a century of dominance, is drawing to a close. The turbine era for light aircraft isn't coming. It's beginning right now.